appreciate that question. So affinity, as I said, if I do not say in the question, that means it is assumed that it is they both drugs have both drugs are full agonists. They both have high affinity or in equal affinity for the receptor. Okay, if I explicitly said that one drug they both are full agonists, but one full agonist has high affinity, other full agonist has a low affinity, like you can see in this particular plot, then yes, then you have to think accordingly, because then if the full agonist which has a low affinity, yeah, that would be that you need more dose to produce the same efficacy, to produce the same height of response.
Thank you.
Follow?
Thank you.
Right? Because this has low affinity, that means that it will bind less to the less receptor, because it won't bind to the receptor that tightly, so that's why it will produce response, but it will be the response that is produced by the low affinity, but full agonist will be smaller than this response, full agonist and high affinity, if the dose is same. Okay, but if you increase the dose, like in this case, then you can achieve the same response. Everybody clear? Everybody clear on that, right? So in this question, when I said that, you have to assume that, because I didn't say that one has a high affinity, one has a low affinity. So you have to assume they both agonists have full affinity, high affinity, and equal affinity on the scale, and that's why they both will result in a same maximal response when they activate the receptor. Okay,
Dr. Shah, can I ask
this
a
is an
question?
example. One second. This is an example that they both are full agonist, but one is high affinity and other is low affinity, and for that's why you have to use more drug concentration with this particular full agonist, because it is a low affinity, and in order to achieve the same response, you have to use more dose for this particular DRC drug. Okay, go ahead now.
Is ED50 the same as the affinity for the receptor, or is that something different?
That's different. That's a whole different thing. And hold that thought, Jennifer. We're going to go on that as well. Okay. Hold that thought. Okay. Maybe in connection to that thought, I can answer you quickly, because it is not plotted here. We didn't plot is ED50 here, but it is there in the upcoming question. But anybody can tell me based on this. Look, we look at ED50 or EC50. EC50 or ED50 is a marker for potency in a simple term. Okay. So anybody can tell me, okay, I know this is a low affinity. Which agonist is more potent here? Which is more potent, the open circle one or the closed pink circle one? Which has more potent?
The open circle one?
Exactly, because you need less drug concentration to achieve the maximal response here. So this is more potent and this is less potent. That's why you have to use higher dose compared to this particular drug DRC in order to achieve the same maximal response. As you can see here, you can achieve the same maximal response with this particular full agonist, but you have to use high dose because it has a low affinity to the receptor compared to this particular drug. Okay. Is everybody clear? Any question? Yes, Himasi.
Hi. I just wanted to
Are you from which campus are you from?
I'm from the MS program.
From Middletown?
No, Harlem.
Okay, so make sure you explain that. Tell me that.
Oh,
okay.
Sorry. Okay. Just does the affinity relate to the potency, or those are two different? Like they don't have a relation to each other?
But indirectly, yes, as I just said that, because in this case, these both are full agonists, right? So, but one has a high affinity, other is a low affinity, so that makes their potency different, right? Himasi?
Right.
So, to answer your questions, yes. Indirectly, yes, because affinity make a big difference. If the drug is same, they both are full agonist, but one has high affinity, other has low affinity, that makes a difference in potency, as you can see here on this plot.
Can you have a full agonist that has two full agonists that has high affinities but two different potencies? Is that possible?
That's not possible. Tell me why. Anybody can tell me why. That's a very good question. I love that question. Where would you see both DRC? If both are full agonists, like in this question, and they both have a high affinity, same affinity, and if you want to draw DRC for two different drugs, same full agonist, same efficacy. Well, what if you want to draw DRC? What will be the position of DRC on that plot? Yes, Nika.
They will be the same line that will overlap if they
I
have the same.
love that. I love that. They will superimpose. They will overlap because they have the same high affinity. They both are full agonists, so they will produce same maximal response, and they will overlap. Now you got my point. Thank you so much, Diego. And a good question. What's the name? MSC. I like your questions.
Thank you.
That's the reason why I want to make it interactive, and I want you to ask me questions. So it will open up the avenues, and it will open up, and clear your any doubts. That's what we are here together today. All right. Yes.
I'm not sure if anyone remembers, but they use a different name on the questions that they sent for competitive agonist.
Yes.
Is there a different terminology for it that is other than competitive inhibition or competitive agonist?
Well, hold that thought. When we get to that question, you can ask me, okay? Because then students can follow that, okay? All right. So anybody can define affinity quickly. What is affinity? We talk about affinity, potency, and efficacy so much. What is affinity? Yes, Alisa.
The strength of the drug binding to the receptor.
Very good. Ability of the drug to bind to the receptor, but that is based on how tightly or how strongly the drug binds to the receptor. That is called affinity of the drug to that receptor. Excellent.
Can you define that as like the amount of substrate that's needed in order to get to the max?
I'm sorry, I didn't understand the question. So
Would you be able to define the potency as the amount of substrate that you need in order to get to the Vmax or like the max?
You are right. That's the best way to define. I agree. And okay. I'm going to talk about potency, but okay, to make it more technical, to make what you said is very simple language. You are correct, because that's just a comparing of the drug, how much drug is required, or drug dose is required, or drug concentration is required to achieve the same maximal response, right? That's how you said earlier. That will give you the idea about comparison of potency, which is more potent, which is less potent, because you go to achieve the same response. Then obviously you have to use different dose of the drug. Based on the nature of the drug. If the drug has a low affinity, or drug is partial agonist, you all have to take this into account. But you are correct. So basically, the position of DRC, the position of DRC on the plot, on the axis, and if you extrapolate this to the x-axis dose or concentration, that will tell you that's the index of the potency. Okay, Anas, that's the index of potency. The position of DRC. We compare to each other, and then when you extrapolate this concentration, that is called EC50 mainly, to the x-axis, that will tell you that's the index of the potency for that particular drug. Okay, so we always take EC50 as a marker to indicate what is the potency of the drug. Okay, EC50 is a standard marker that we use to compare potency, or to dictate or determine potency for each drug, and then you can compare. All right. So, okay, you define potency, I define potency now. What is ED50? Anyone, ED50? Anyone?
The response that's received 50% of the time.
So that's a dose that produces 50% of the maximal response, right? ED50. Same like EC50. So ED50 here is actually potency. You can see this is another way to define potency. So we put it EC50 is concentration and D for dose. So the dose that is required to produce 50% of the maximal response in the system is ED50. Okay, so that's ED50. What is ED50?
The toxicity.
So toxicity what? What is toxicity?
The amount, 50% of the time that you're gonna, basically the level that you're gonna get the toxic.
So the amount of the drug, right, or the dose of the drug.
Sorry,
right?
Yeah.
The amount of drug or dose of the drug that is required to produce 50% of the toxicity in 50% of the taste population or animal, right? That's ED50. Clear? All right. All right. So we are pretty okay. Now, how would you define efficacy in a technical terms? We talk about efficacy, that how would you see efficacy on the plot, right? And we talk about that in details. What exactly is efficacy? We talk about that it will produce maximal response. How do you define that in a technical terms? Yes, Andrew.
Oh, sure. Would it be when 100% of when the amount of drug in the system is creating 100% of the response needed?
Right. So it will induce conformational change in the receptor. Right? Once the drug binds to the receptor, it will induce conformational change, and that will activate the receptor. And that activation of receptor will result in certain pharmacological response in the system that is called efficacy. Right? It will elicit or generate a certain pharmacological response. When the drug binds to the receptor, it will induce conformational change in the receptor. That will in turn will activate the receptor, and the receptor activation will result in post-receptor binding events, and that will eventually result in generation of certain pharmacological response in the system, and that is called efficacy. That is called efficacy of the drug. Okay. All right. All right. All right. Now I give one example here, and I know you have. It is a little premature to discuss because I always but I always want to give some context. Without context, it's not fun, or it's very difficult to understand the information material. Or you will feel that, or I also feel that you are learning this information in the vacuum if I do not give an example of the drug to understand the concept. So I put it something here, as you can see in the bottom. Efficacy and affinity, they both are independent variables. Drugs which have the same affinity can have a different degree of intrinsic activity or efficacy, and vice versa. So give me an example of the drug. You don't have to give me the name of the drug, but just give me a name like with an agonist or antagonist that have a same affinity, but have a different efficacy. Why I made that kind of statement here? That's my question here. What is the interpretation of this statement based on what we discussed on Wednesday and today in last 20 minutes? What do you interpret this based on this statement now? Yes, Andrew.
Oh, I didn't know that was a question. I was going to say it sounds similar to a non-competitive antagonist.
Yeah. So again, when somebody answer the question, I want full answer, not partly answer, because this is physiology, and I want to know why beyond each and every explanation, or when we discuss anything, any concept, I want to know why, and I will explain that why also at the same time as a teacher. I want to know why behind each and every concept. Like, okay, my question is that how would you interpret this statement? Give me example of that. I don't want you guys to give me a drug example. If you can give me drug example, that would be really great. If you cannot give me the drug example, you can simply tell me how can two drugs have a same affinity and no efficacy. If I can make it simple, or same affinity, but one has a high affinity, high efficacy, other has a low efficacy with same affinity. Give me an example of that. Because we discuss agonist, partial agonist, and antagonist. I'm giving you a hint now. So give me a two drug that have a same affinity but would have a different efficacy. Yes, Rigo.
Would it be like a beta blocker? It does have affinity for the receptor, but it just doesn't perform the action.
Good. I love that. Good. Because I guess, yes, and I gave that example too in the class. Good job, Diego. So if you take one full agonist and one antagonist, full antagonist, you can say, if you want to say that. So they both have same affinity for the same receptor, for example, okay? You take one full agonist, one antagonist, and let's assume that they work on the same receptor, okay? So one full agonist, one full antagonist, they have a same affinity for that receptor, but full agonist will have 100% efficacy, like here in this plot. You can see full agonist can give the full response with full affinity. So, but with antagonist has a full affinity, but it will not produce any response. It has zero efficacy. That's the best example I can give you. And clinical example, and Diego said that The agonist is norepinephrine, for example, which will stimulate beta 1 receptor in the myocardium. An antagonist is beta blocker, metoprolol or atenolol, that can block that beta 1 receptor and will not produce any effect, but it will just block the effect of norepinephrine that can result in increase in heart rate, for example. So when you give beta blocker to a patient who have an increased tachycardia or increase in heart rate, when you give that drug, it will oppose the effect of agonist and will not will help in decreasing the heart rate. Okay, so that has two different, that they both have same affinity but different efficacy on the same receptor. Everybody is clear? Any follow-up question?
Yeah, quick question. So this is
Yes.
Sterling from the Harlem campus.
Yes.
So would efficacy only be referring to a positive effect on the protein when binding to the receptor? So an antagonist can't be effective if it's having a negative effect?
Well, I mean, you can use that way, you can remember that way, but I don't think, I mean, it's not an ideal language we use. It's not, we do not use that kind of language in pharmacology. So I cannot say that as a professor, but if you want to remember that way, you can remember, because antagonists, and I know you are from Harlem campus, so I understand, because I talk about that on Wednesday. I was very loud and clear to my students on Wednesday class. Antagonist has no efficacy. Same affinity to the agonist, like agonist, but antagonist or blocker itself will not produce any pharmacological response in the system.
Okay, got
it. It has zero efficacy, but so then what is the job of antagonist? Then Dr. Shah, then why we are, you can ask that question to me, then why the hell we are talking about antagonist here? Antagonist will only block the effect of agonist on the receptor. It will only block the site on which agonist binds, okay, and will not let agonist to do its job. Sterling, you follow? So that is the only job of antagonist. Antagonist itself doesn't produce any effect, but it will just inhibit or block the effect of agonist on the receptor, and that's why we use antagonists to treat certain clinical disorder.
Okay, got it. Thank you.
Okay, no problem. Good. All right, let's move on.
Dr. Shah, if you're on campus, the fire alarm is going off, so students have to exit at this time.
Oh. All
We
right,
will
so
connect to our phones.
If you're on Middletown campus, you have to exit the building. It's a fire alarm.
All right, then I can wait. Or I'll be on the Zoom. I will wait. Oh yeah, anybody has any questions? It is being recorded, so I can answer the questions rather than talking about new information here. We'll wait for the people to come back, but anybody has any questions, please feel free to ask questions to me. Again, it shouldn't be any confusion here. It's pretty straightforward concept, and I repeated a few times in the class, and I repeated today again. And I think it's clear to you guys. Looks like that. Students who ask questions, they ask legitimate and logical questions or logical follow-up questions that make sense to me. It looks, based on that, I can interpret that you have an understanding of this concept now. But if you still have any question on affinity or efficacy or potency or whatever it is, I'm more than happy to answer questions to you.
Hi, I had a question about the concentration, about the steady state concentrations, and
yes, love.
How to go about calculating that, with like clearance and infusion.
Oh, that was the question on the loading dose and maintenance dose part, right, love? So you can hold it. I recorded that session from last Friday and I posted it, but I'm more than happy to answer it at the end of this session.
Sounds good, thank you.
That's a whole different thing than this concept. So yes, I'm happy to go around that. And as you probably know, since I think you were there last Friday, right?
Yeah.
Okay, so we talk about that. So I'll go over on that again, that concept, okay?
Okay, thank
But
you.
it is very good question. It is very important question for all of you to know this, how to calculate the maintenance dose and loading dose, and where you have to put where you have to factor clearance in this calculation along with the target plasma concentration, right?
I had a question. So for in competitive inhibition, the efficacy will stay the same, but the affinity will change. So it's just like, it would be the same thing as like competitive inhibition of an enzyme.
If I heard you correct, you are correct. Efficacy, this is Vmax, right, in competitive antagonism, right? And this will remain the same, right? Right?
Okay.
But the EC50, which is called Km in a biochemistry language, that will change, as you can see here, which is called EC50 or potency.
So in non-competitive, the Vmax will change. So that's like the affinity.
Vmax is efficacy, not affinity.
Vmax is efficacy. Right. Okay.
This is called efficacy, right?
Yes.
This is efficacy, right?
Mm-hmm.
The response produced by the drug is efficacy. Maximal response is this one. So again, one of the reason I see that, which I would prefer not to use the term that you learned in biochemistry, substrate. I will say that I will make sure that I'll just make connections to biochemistry, like EC50 is Km and Vmax is efficacy. But I prefer you guys not to use the term like substrate and all, because we are not, it's not biochemistry, it's pharmacology. I want to use the term drug. Okay. Like it's more used for enzyme and biochemistry stuff. So, but I'm happy to connect it with the biochemistry here. Otherwise it will create confusion to you guys, as you just had this you just had this problem that you are mixing up with affinity and efficacy. So efficacy is Vmax. Remember that, write it down. Vmax is maximum velocity of the reaction of the drug. Vmax, that's called Vmax, right? Velocity of the reaction, maximum velocity of the reaction. In this case, it's a reaction of the drug. It's the effect of drug. And Km is a rate constant of reaction in biochemistry, which is equal to EC50 or called potency. Okay, that's called Km. Km is rate constant of reaction for enzyme language, but in pharmacology, we use the term EC50 or ED50. That is a marker for potency of the drug. Okay, NS, clear?
Yeah, thank you.
But you are correct. You are correct that efficacy will remain the same in competitive antagonism, and efficacy will be decreased in non-competitive antagonism. You can see it here, right? So maximal response is suppressed as you move from left to right in non-competitive antagonism, but the Km or EC50 or potency will remain the same. You see this, right? EC50 will remain the same in non-competitive antagonism, but EC50 will be different in competitive antagonism. All right, while we are waiting for other students to come, let's talk about this particular plot. It is being recorded, so nobody is going to lose any benefit of that. Now, based on that, what we discussed, can anybody tell me, and this plot is very clear, it will show you the efficacy. Efficacy is, as I told you, on the y-axis, the percentage maximal response. So this, you can make an arrow like this, and this is the efficacy, okay? And this is the maximal response, maximal efficacy of the drug, and that's the maximal response drug can produce. And the dose that is required to produce maximal response is called ceiling dose. Ceiling dose means this is ceiling. You cannot go beyond that, ceiling dose. And this response is called threshold response or ceiling response. Okay, it's called ceiling response, and the response produced by the drug is called ceiling dose. That's the maximal response produced by the drug, and that's called efficacy, maximum efficacy of the drug, of the full agonist, for example. So this is called efficacy on the y-axis, and on x-axis, as I told you, is a potency. Okay, this is potency. So the position of DRC, as you can see here on this plot, in connection with the x-axis, is an index of potency. The position of DRC on this plot in connection with the x-axis dose or drug concentration is an index of potency. Okay, because when we take this EC50, we extrapolate this from here to here to find out the drug concentration, that how much drug concentration is required to produce this particular response, or EC50. Okay, this is so tell me which is more potent here based on this plot now. Which is more potent? Whether it is yellow color, the red color, the blue color, or green color. Yes, Andrea.
So the red one would be the most potent because it requires the least amount of drug to achieve the full efficacy.
I love this. That's called complete explanation of the question. Thank you, Andrea. Thank you so much. So now the blue, which is called epinephrine, and again, you don't have to remember the name of the drug for the exam. Since it is there, it is here, I'm just telling you that. So the blue curve, DRC, is epinephrine, and that has intermediate potency, right? And this is the most potent, and the green one is the least potent drug, which is norepinephrine. Okay, because that you have to use more dose to achieve the same maximal response with the green color drug, which is norepinephrine. So this is least potent compared to other two DRC here. Okay, now why we take this EC50 into account to find out the potency or to find out the drug concentration, to measure the drug concentration for that particular drug or dose response curve. Why we only take EC50 into account? That's a hard question. We discussed about that in the class. So I'm sure some of you or maybe all of you knew about that. So if anybody knows about that, why only we take this particular midpoint in the dose response curve, is called EC50. Why we take EC50 into account to measure the potency of the drug? Why that's a standard indicator or marker EC50 to measure the potency of the drug? Why we look at EC50? Why not EC100, EC70, EC30, EC20? Why we do that way?
Hi, this is Daphne from the Harlem campus.
Yes.
Is it because that's the straightest part of the slope? So because it's a straight line, it's the most reliable place to measure?
What's your, I'm sorry, which campus you are from?
I'm from the Harlem campus. My name is
What's your name
Daphne.
again? I'm sorry.
Daphne.
Oh, very good, Daphne. Good job. So again, can you repeat one more time, please?
I believe it's because it's the straightest part of the line. So the slope is a straight line. So therefore it's the most reliable area of the graph in order for you to measure.
Very good. I love that. I mean, you're right. I don't want to use the word straight. You can say straight in this way because it's a straight like this, but I want to use the word steep and linear technically. Okay. So this particular portion is more linear. This particular portion is more linear and more steep because there in this particular area, there is an optimal drug receptor interaction. Stephanie, you follow?
Yes, I understand.
Okay, good. So and especially EC50 is the point where there is a perfect drug receptor optimal interaction. One drug molecule, one receptor. So that's very ideal, accurate, precise drug receptor interaction, and that's a standard measure or accurate measure of potency or the drug dose or drug concentration when we take EC50 into the account, the midpoint of the dose response curve, because that's the optimal drug receptor interaction. If you go above that, the receptor will start saturating slowly, obviously, as you go more and more, as you can see that the curve flattens. The curve flattens, and eventually the curve becomes level off. There's a leveling up of the curve and then become plateau. So that's why this happened, because receptor system will start saturating and the sensitivity of the receptor will be decreased as you use more and more drug as you go above this EC50. Okay, the receptor will start saturating, it becomes less sensitive to the drug. That means you have to use more drug to produce the same response. Okay, if you do not use the more drug, then the response will start flattening, curving, as you can see here, and become more linear plateau and leveling off and becomes linear and straight or plateau here, because now the drug, regardless how much drug you put in the system, it will not result in any kind of more response. This is a steady line now, straight line, plateau, level off. Okay, because all the receptors are saturated, occupied at this particular range in this system now. Okay, so that's why we take EC50 into account, and that's a standard marker or measure of potency for each and every drug, and you can compare that easily on the plot when you have more than one drug. All right, so that's good. You got it. Why we take dose response curve? Anyone quickly? Why not arithmetic numerical? Oh, okay. So you guys are back. Very good. So why we take dose response curve on the log scale? Yes, Alicia.
Because the concentration of drugs can be so different, so we want to have like a unified way of comparing them.
Very good. So you can easily compare and contrast, and you can put multiple data, right? You can incorporate multiple data, because if you look at log scale here, it is in exponential range, right? It's an exponential growth. raise in exponential fashion. So that's why we take DRC in log scale, so you can have multiple data on a small space, and you can easily compare and contrast between 2 or 3 or 5 or 10 or 100 curves, 100 DRC, right? So that's why we take in a log scale, because it's exponential in an exponential fashion. The drug concentration increase in exponential manner on the x-axis. All right. All right. Everybody's back. I'm still all right. So we can move forward now. So in this particular case, and we talk about that both can achieve the same maximal response, but they both are full agonist. But despite they both are full agonist, this particular agonist, which is close pink circle, DRC, requires more drug concentration because this has a low affinity compared to this one, right? So that's why this is shifted on the right side compared to this open circle one. Okay. All right, I'll start the poll now. Yes, good. No, Erin, don't worry about knowing the name of the drug because I'm seeing the chat now. Don't worry about that. No need to know the drug, okay? It just gives you some context that why you are learning it. It will apply. It's just application of the concept, or it will tell you why you are learning it. There is a reason why we are discussing it, because you have to apply this concept in a clinical medicine going forward. So that's why I just want to give some example. No problem, Miss Abraham. Thank you. Again, don't be shy asking questions. It's an opportunity for you guys to ask questions. I see some DO students. I see a lot of DO students, but I see some DO students who are from a former MS program, and they did so good in the program. Despite that, they are here. They don't have to be here, and I would not mind if they don't come. But despite that, they are here. They did so well in the MS program. They excel in this course. They proved themselves that they are very good. They're excellent candidates. They are in the DO program, and they don't have to come on this supplemental. Despite that, I saw some of them on the supplemental side, and that makes me increase my drive to teach. There are so many. Amanda, I see Vishal. I'm sure there are the people I'm not able to see everybody on my screen. But I see Vishal for sure, and Amanda. They excelled in the master's program. Excelled. Not only made the GPA, but excelled. And I'm sure there are other MS students, MS Studio students too here. And I'm not able to see everybody, but I'm sure they may be here too. All right. Yes, I already posted the list of the drugs on Canvas because I saw someone chat. It's already there. Whatever you need to know is already there up on a Canvas on a toolkit. I see your new DO students. I think they did well, and despite they did well, they are here. It's not required for them to come. I appreciate that. I certainly appreciate that as well. All right, I'm going to end the poll in 5 seconds. 5, 4, 3, 2, 1. I'm going to end the poll. Share the results. Very good job. Any volunteer explain me that? And this will also answer some of our questions. Actually, I answered that, but we discussed it in the previous slide about the affinity and intrinsic activity or efficacy. So I just put it here for you guys to make your life easy now. So yes, go ahead. Any volunteer here?
I can go. That's okay.
Of course, yeah. Thank you.
Okay. So competitive antagonist, so will bind to the same site as the agonist, and then it will be reversible because if you add more agonists, then you can reverse the effect. So the inhibitory effect can be reversed by adding more of the agonist.
Very good job, Amanda. Great job. Anybody can tell me which drug is antagonist here? And no, not to you, Amanda. I just want someone else to answer it now. You answered it correctly and fully appreciated. Thank you. Which drug is antagonist here? Villain, like villain. And which drug is agonist, like hero? I saw Miss Abraham raise the hand first, and then I will come to you, Erin.
You want me to answer both or just one so the other person can answer one? Or?
No, you can answer, and then I'll maybe
okay. So
yes.
drug Y is our antagonist, and then drug Z is our agonist.
Very good. Now let's move to Erin. And Erin, can you tell me, if you don't mind, why she said that drug Y is antagonist and drug Z is agonist? On what basis you can say that it is drug Y is antagonist and drug Z is agonist? On what basis you can say that?
It's because when drug Y is present, we need 3 times of a higher dose. So essentially, we need more drug Z when drug Y is present. So drug Y is the competitive or antagonist.
Right. You are right. It is competitive also because they bind on the same side. You are correct. And why it is reversible? Because as you said earlier correctly, and you and Amanda and Ms. Abraham, that when you increase the dose of drug Z, which is agonist, by 3-fold, it can displace the drug Y, right? Right? So what does that indicate? It indicates that it is competitive and reversible. That means they both compete on the same side, same binding sites on the receptor, and drug Z, when you increase the dose of drug Z 3 times, then it has the ability to displace drug Y from the same binding sites, and that will result in you can achieve the same maximal response, as you can see here, in the presence of drug Y, for example. So suppose, let's assume this is drug Z by itself, and then if you want to achieve the same maximal response with drug Z, but that is in the presence of antagonist Y, then you have to increase the dose of drug Z here, agonist, in order to achieve the same maximal response. So that indicates it's a competitive reversible antagonism, and you can see the same level of response on analgesia in 25% and 75% of the subjects tested here. Okay, that indicates that this is a competitive reversible antagonism. Yes, Sterling. Yes, Digo.
I was just I'm sorry, go ahead, Digo.
No, you go ahead. You were first.
Okay. I was just asking, but people are responding in the chat. But I was asking which clue in the question stem implies that it's not an irreversible antagonist.
Because as all the students said, that those who participated, you can see the same. Look, this is the key word. I didn't highlight in the red, to produce the same effect. This is the key word here, right? The key sentence is here. You can use 3 times higher dose of agonist drug Z, Sterling, to produce the same effect, right? That indicates that it is a competitive reversible antagonism. And you can see the same response at the level of 25% and 75% analgesia. Does that make sense, Sterling?
Yeah, that makes sense. Thank you.
Thank you. Digo.
What would the graph look for options A and B?
Yeah, I'll go on that. Good point. And that's why I showed that graph. So option A is what? Agonist with full efficacy, right? Oh, that we talk about that. You're talking about answer A and answer B or what? Hello?
I'm sorry, repeat your question.
What can you repeat your question?
No. You asked something about a survey?
Huh?
Never mind, sorry. Go ahead.
Okay, I thought like you were asking about A and B. I would show you the A also here in the. So It's A is here somewhere here. It's A is coming up in the next question. I'll hold that thought. I'm sorry, B. We talked about A already. B is a partial agonist. So what do you expect in terms of response of partial agonist?
A partial agonist would not be as reach full efficacy.
Exactly. So I put it here. It has the same affinity like a full agonist, right? But it has a sub-maximal intrinsic activity or efficacy. So response will be smaller or lower than full agonist. You follow?
Yep.
Good. Yes, Daphne. I don't know
Hi, thank you. Daphne, yes.
Yeah, sorry.
No, it's fine. So basically if it was a irreversible, there's no amount of drug you could have given in order to overcome that particular effect, correct?
You are 100% correct, Daphne.
Okay,
100%.
thank you.
All right, good job. Good job. All right. So A, obviously we talk about A. So I spoke so much about A. So you know about A agonist with full efficacy. That means it's full agonist will give the maximal response. Partial agonist will give some response, but it will be sub-maximal response. It won't be maximal because it is partial agonist. Okay, partial agonist will always have a sub-maximal response compared to full agonist. It's because partial. It loves partial. It has partial effect on the receptor. So that will produce a sub-maximal response. Same affinity, but sub-maximal response. Non-competitive antagonist and C, D, and E will discuss here on this plot now. So who can explain the characteristics of the competitive antagonism here briefly? What are the three characteristics of competitive antagonism? And we talk about that. Somebody asked that question earlier to me. How would you define competitive antagonism? What are the three classic characteristics of competitive antagonism here? That's a major characteristics, I can say. There are 5 classic, but 3 are major classic characteristics of competitive antagonism. Anyone can tell me. And we should have talked about that. It's not new that I'm asking. Anyone? I don't know who raised their hand first. I see Daphne. Daphne, you want to go first?
I can tell you 2 of them. I know they have differing, they have the same Vmax.
Very
or
good.
the same efficacy.
Efficacy. I would like you guys to use the word efficacy.
Sorry,
Right.
same efficacy, and they may or may not have the same. No, they do not have the same potency.
Very good. Very good. Okay, so those are like same efficacy. We talk about that. When you increase the concentration of agonist in the presence of antagonist, you can displace antagonist and can achieve the same maximal response. And that's why the efficacy is same, right? In competitive reversible antagonism. Good. And the potency or EC50, or you can say Ka, a biochemistry language, but I don't want to use that term often that. So EC50 or potency will be different in competitive antagonism, but efficacy will be the same. I agree with you that completely. You're correct. What else? Anyone else, please? Alisa.
The slopes are the same, so the rate that the drug binds to the receptor to reach the efficacy would be similar once you increase the potency.
So how does that reflect on the curve?
They have the same slope.
Same slope is more technical term, right? That's what we talk about. But what does that indicate? You actually answered difficult part here, Alisa. But how do you see that on the picture on this particular plot? When you compare that?
That the affinity is the same?
Well, it's the same agonist, so affinity has to be the same, right? Antagonist will make the difference here. Then that's why you have to use more concentration because antagonist will inhibit the effect of agonist, right? Same agonist with same affinity, obviously. But antagonist is preventing the effect of agonist. That's why you have to increase the dose of agonist, right? To displace antagonist to achieve the same desired maximal response, Alisa, right? So, but my question is that what are the characteristics when you see this on this plot, or based on the same slope as you can see? Like, what do you see this here on this plot? Anybody can answer that. So Alisa is correct, but I just want to elaborate that. Like what you see here, which we talk in the class as well, and I don't blame you. You can remember everything in one shot. Yes, Michael.
I forget the exact term for it, but it's like a parallel shift of the graph.
You're correct. I love you. I love you, man. I love you. So the shift is parallel, right? The shift is parallel, as you can see here. And Alisa answered a difficult question. This is there is a shift is right word. That's number one characteristics, Michael. The second is the shift is parallel. So if you look at all of these three DRC, they all are parallel to each other and one another. Agreed? Okay, now Alisa said that how can you say that it is a parallel shift? The rightward shift, you can see it. I mean, anyone can see it. My 13-year-old daughter, she's just 13 years. She will be 13 now in October. She can even say that this is rightward shift. Okay. She can probably also say that it is a parallel shift. But here is my question. How can you say it is a parallel shift? Why I said that it's a parallel shift. Rightward shift, you can see it. It's not a big deal. How can you say it is a parallel shift?
Is it because the slope is the same?
Slope is the same. Very good. So if you take any two corresponding points, if you take a point between A and B here, and same corresponding point here and here, if you measure the slope m, the m value, m is equal to y over x. If you measure the slope technically, mathematically, they use mathematical modeling now. With all latest tools and technology now, it's more advanced now. They use this mathematical model to quantify the level of slope. Based on that, they can see that they can say that with confidence, with accuracy, precision, that the shift is not only rightward, the shift is also parallel, because the slope of each of two corresponding points on each DRC is exactly identical, same, ditto same. That's why they are parallel shift, not only linear, not only rightward, but parallel shift. What is the third one that you said that students, people said that, but how can you say in a technical term that how can you say it is? What is the third characteristics of the competitive antagonism? And someone said that efficacy is same, right? So that means the response is surmountable. The response is surmountable. That means you can achieve the same height, same response when you increase the dose of agonist. So that's why the response is surmountable. The response is surmountable. That's a classic characteristics of competitive antagonism. Now, anybody can tell me quickly what are the three characteristics compared to this in non-competitive antagonism and why? MS students and DO students who have C plus and below, they have to stay here on the supplemental. It's required for them. Okay. But rest of them, those who want to leave, they can leave at 2 o'clock. But I just want to finish. I want to help them the best I can. So anyone can tell me what are the characteristics of the non-competitive antagonism? Quickly. If you put in the chat, I cannot see in the chat. I have to see it now. So much chat. Anyone? No problem, Amy. Our course rep, Vishal and Alan, they are very good, very helpful, and very active course rep. So I'm sure they'll be happy to share the Zoom link of the Friday supplemental with you guys and Montana campus as well. No worries about that. We want to give equal opportunity to have all students to learn this. No worries about that. Thank you, Vishal. Anyone, please.
I can do this one, Dr. Shah.
Thank you. Appreciate it.
No problem. So you just want the characteristics of non-competitive inhibition, correct?
Yes.
Okay, so basically, whenever you give drug, it'll bind to a receptor, but a non-competitive inhibitor will bind somewhere other than the receptor. And
Very
then
good.
It also lowers the efficacy of the response.
Right.
And no matter how much more drug you add, you cannot overcome the response at all.
I love that. So in a non-competitive antagonist bind either irreversibly which is called bicovalent bonding. When somebody, you learned that in chemistry, all of you, I'm sure. So when something binds with a covalent bond, it is very hard to detach or break that bond. It's called covalent bond. Okay, so that covalent bond. So in some cases, antagonists bind, create a covalent bond on the same binding sites on which agonists bind, and that's why agonist, regardless how much you increase agonist concentration, agonist cannot displace the antagonist, because antagonist has bound irreversibly with covalent bond to the same site on which agonist binds. So if you increase agonist concentration in that scenario, regardless how much you increase it, the agonist cannot displace antagonist, because antagonist has bound to the same site with covalent bond. Very strong covalent bond is called irreversible antagonism, or inhibition, you can say, or antagonism, same thing. So that's number one. Second thing, as Andrea said, the binding sites could be different. Antagonists bind to a different site, which is called allosteric site or adjacent site. So on which agonist doesn't bind, the agonist will bind to a different site. Antagonists bind to an adjacent site or allosteric site, and agonists bind to a different site. So there is no competition. That's what's called non-competitive, and that's why the agonists will not be able to inhibit the response of antagonists, because they don't interact directly. They bind to the different site. Period. Okay. So if I want to classify that three characteristics here, as Andrea said, the efficacy, the maximal response, as you move from left to right, there is a rightward shift, little bit you can see here, but the maximal response or efficacy, as Andrea said, will be suppressed or decreased in case of non-competitive antagonism. So maximal response will be suppressed as you move from left to right in non-competitive antagonism. The second thing is that the response is not parallel. Okay, the shift is not parallel, right, Andrea? The shift is not parallel, right? And obviously the EC50 or you can say potency will be the same for in all 3 DRC, in non-competitive antagonism. That will not change, right? Efficacy will be decreased, but the potency will be the same. EC50 will be the same, but right, there is no parallel shift, and the maximum response will be suppressed as you go from left to right. So it is not surmountable. The response is not surmountable, non-surmountable. Okay. All right, let's move on. I'll start the poll now. So this will be very quick discussion now for this question. And I think next question also we can finish in probably next 10 or 15 minutes. Okay. And then I'll let you go to study other subjects as well. But those who want to leave, it's only 2 o'clock. Feel free to leave. I'm okay with that. At DOMS, please feel free to leave. It is being recorded. You did your job. You came in the class. It's required for MS. So I see all the students came, and they can leave if they want to leave. Radio students also can leave. It's already 2 o'clock, so you are good to go. I'll just complete this and next question. Again, don't be shy reaching out to me. I'm very open-minded, very approachable, friendly professor. Okay, and I'm telling you upfront, it is being recorded. Okay, this is my 11th year here. Students know me by this time, that how approachable I am, but I'm still repeating it. You being a new students, please email me. Don't hesitate. I cannot meet tomorrow because it's a Jewish institution. So for a religious reason, I cannot meet tomorrow. But that's why I'm going to meet on Sunday. Okay, with respect to religious, all religion. I don't want to meet tomorrow to anybody, but Sunday we can meet. Okay. It's a Jewish institution, so we have to follow that policy. But Sunday we can meet for sure, 12 to 1 and 5 to 6. All right, I'm going to end the poll. It's pretty straightforward question, but you have to know this now and for the future as well.
Victor Shaw, question while everybody answers. regarding the previous week pharmacokinetics, how much regarding the problems, the mathematical problems like plasma concentration or volume distribution, we are of course supposed to learn that, but will there be like a workshop for that or some extra resources, extra questions that we can find somewhere?
Well, I cannot believe that you are asking that question because there's so many questions I posted. 6 or 7 Q bank, right, Diego? We talk about that. I said that in the class. So it has so many questions, math questions, that I don't think the students can finish that. It has so many questions which are posted to practice, which are all heavily based on math. It's a 6Q bank, if I'm not mistaken, and they all have some kind of math flavor. Okay, and I'll be doing on Sunday. You can come and you can ask questions to me. We talked about that last week on supplemental, which I posted the recording on loading dose. But it's a good thing you brought it up, Digo. So let me repeat it: loading dose, maintenance dose, VD, and PKPD modeling, pharmacokinetic modeling, drug distribution are very important for the exam. Okay, on all the questions that I have posted on Canvas, as I said multiple times to you guys, they all are important, and you have to practice that to do well on the exam. Okay, and I posted that with the answer, so you can do it quickly. Once you practice once, you don't have to do math again and again. You can review it again second time. Quickly just review that. Rather than writing each and everything again and again, just to save your time, because I know you have to prepare other subjects as well. But there are way more than enough questions to practice on Canvas. Too many questions, math questions. Okay. All right. Who can explain this concept?
Well, I could possibly take a stab at it.
Yes, Andrew.
Oh, yes. So basically, for therapeutic index, the equation for this would be TD50 over ED50. So basically, when half of the dose is toxic versus when half of the population experiences a basically an effective dose. So you just divide those numbers, 200 by 20, and you get 10.
And how would you interpret? I'm not asking you. Anybody can answer that. How do you interpret this result? This calculation. What do you mean by 10? Anyone?
Does it mean like you could give 10 times the dose of that drug without being toxic to the patient?
Superb. I love that. Good. So the drug is safe to use up to 10 times, right? To the effective dose, right, Jasmine? So you can give 10-fold more drugs,
Yes.
with effective dose, and despite that, it will be still safe, basically, to use that drug in the patient, right? If you go above 10 folds, then you will start seeing toxic effects, right? All right. Everybody clear? It's a ratio of TD50 to ED50. So logically, that itself indicates that you can increase the dose of drug up to 10 folds and still it is safe to use in the patient. That's called margin of safety of using any drug in patient. It's called therapeutic index. And we talked about that also last supplemental, briefly about that as well. Okay. So you can review this slide. Okay. And the last question, and then I'll let you guys go. Okay. Those who want to go, they can still go, as I said. And now you can answer these questions also, because we talk about all of these some way. Diego, you have access to the Q bank, right, sir? Or the Q bank?
I'm looking for it right now, but unless I'm blind, I really cannot find it.
No, it is with each week, like after week 3, week 4, and the toolkit. I'm sure I published
definitely
it.
blind. I did find it now.
Then I'll double check because I published it. It is like, look at after week 3 and week 4, like with each week, each week, sub weeks, basically. There are 2 sessions for each week, right? You cannot see the Q bank? Anyone else?
Yeah, no, I definitely cannot see that question bank. I'll double
Like
check
Q
again
bank
with someone.
A, Q bank B, Q bank C, Q bank D, Q bank E.
Nope. Let me see. Let me check again. Sorry.
No, then I have to double check because I know I published it. Your students, you can see it or not?
I can see it.
I
Okay.
can see it.
I can see everything except Q bank B.
For the masters or DO?
I'm DO.
Okay, so I'll make sure that it is there. If it is not published, I'll make sure I'll publish it. Okay. And masters, other students, you cannot see it either. I have to double check it now. Can anyone verify with me, please? Master
Yeah,
students,
we can see A and C, but
you can see A and C. You cannot see B and D.
no.
Okay, I'll double check it. I'll make sure I thought I published it. I double checked. 3 times I checked it.
A, C, and D is there. I'm not sure about B. I don't see B.
And what about E?
Okay, I found E. No, it's a user error, Dr. Shah. Definitely on our end.
I'm sorry, say that again.
No, it's us. I do see it. I do see it now. So
Okay.
Q bank E is up.
Yeah, they're all there. Yeah,
Yeah,
they're
there.
in a different section.
Yeah, the reason I put it different to help you guys better because that connects with that particular right. So that's why I publish it because otherwise you'll be confused if I put all the Q bank together, questions together for 4 weeks, which is actually 4 weeks material. Now we compress it in 2 weeks because up to last year I was teaching it for each session for 1 week because 4 weeks material is too much information. So I thought to divide it for each session. It's a math based, so I don't want people some people don't like math, so I just want to help you guys out. So I thought like let me make it at section wise Q bank to help you guys out really well. All right, so I'm happy about that because I know I double checked. Oh yeah, one thing which I can ask Vishal or Amanda or anyone, course rep Alan. I don't know whether I posted the last year recording or not, if it is accessible, because it could be there, but you may not access it because the Zoom technology or Zoom feature, the school has changed it, so you may not be able to access last year recording. In that case, let me know so I can, because I have downloaded the recording of last year exam review, so I'm happy to repost it if you cannot open that from last year, because the Zoom if it is more sometimes if it is certain after certain time, once the limit is crossed, you cannot review the Zoom recording. So yes or no, can you see that or not, those who have
It was
tried?
accessible for me yesterday. I watched it yesterday, so it worked for
It's
me.
good. That's good news. Thank you for helping me and reducing my work, Amanda. And then I have to do it again. Then that's a lot of work for both programs. So good. All right, I'll stop it and let's discuss this. Good, you are expert now. Almost majority of you answered this correctly. Who would like any volunteer? Why potency? No one? Don't be shy. Yes, somebody raised their hand. Michael.
So the question's saying that the two drugs share the same mechanism of action and the same efficacy. So the only differentiating factor would be potency because full or partial agonist is related to efficacy. Same goes for slope of the dose response curve. And then the other two would also be limit of action and dose for threshold of action. Those would be related to the mechanism of action, right?
Right. Excellent. I love you, man. I love you. Superb. Outstanding, Michael. Outstanding. Outstanding response. Okay. Beautiful. Excellent. All right. So, all right. Anybody? Why A is not the right answer? Anyone? I mean, he said that really nicely. Why is A is not the right answer? What is limit of action? Will that be same or different here? What is limit? I told you limit, threshold, ceiling. What is that? Yes, Andrew.
Well, it's about as far as it's as much work as the drug can do, and since we have the same efficacy here, it's going to hit the same limit.
Yes,
Yeah.
I love you, Andrew, as well. You are right. Limit of action is basically efficacy. It's a different term that we use in pharmacology, like that you use in Vmax for the Vmax in biochemistry. We use two different terms: limit of action or efficacy. It's same, right? So you cannot use that. Good. Why not B? Why not B? Dose for threshold of action. What is that? So you can see this is the baseline, right? You can see it here. Can you see my cursor? Right? So this is the baseline, and as soon as you start rising, this is the threshold dose, right? Threshold dose. At what you can start seeing the response, and it doesn't have to be necessarily the same, right? It could be different, right? So you cannot use that, right? You can see one in this graph too, right? So it doesn't have to be the same all the time. So we can, and it's not a standard way, a standard mechanism to compare. So we do not use B, those for threshold action. Okay, it may be different, it may vary. Okay, so even though it's the same efficacy, the drug has the same efficacy, but it could have a different affinity, right? Same mechanism of action, same affinity, but it could have different affinity. Like in this case, you can see it here, and that's why the baseline will be different here. The action threshold will be different here, and that's why you cannot use that to compare and contrast. So B is ruled out. B is ruled out. Why C? Why not C? We just talk about that. Why not C? Yes, Andrew.
Oh, right. Because I was thinking for two reasons. Because for at some parts on the graph they can have the same slope, so that wouldn't differentiate them there. And then also because they have the same efficacy, that could imply that they're competitive inhibitors, and that their slopes would be the same. So that doesn't work.
Exactly. If the drug is the same efficacy, right? It could be different potency. I understand that, but that's why the potency is the right answer here. But if same efficacy, if the potency is because you can still have same efficacy with two different potency, right? So the slope is same because they are parallel, right? That's why they are parallel, right? Shift, as we discussed earlier, the slope will be the same, and you cannot use that, right? To distinguish it. So that's why potency is the only one which will be different here, and you can use that to distinguish two different plots, right? Make sense? Anybody has any? And E is explained really nicely because if full agonist, full efficacy, partial agonist, partial submaximal response, but they will be the same, right? So that's why E is ruled out. You follow? So because the efficacy is same here, right? So full agonist, same efficacy. Partial agonist, same efficacy. You cannot use that as well. So D is the only answer here. Anybody has any follow-up questions?
I do. So
Yes.
I'm trying to picture this graph. Would it be like, so for example, let's say that the bottom curve at the 10 to the 3 could start just shooting up and cross over the other graph because of the maybe not I'm thinking about potency, but no, I'm just trying to picture how it will be, but not the efficacy, because if the efficacy is the same, they will both reach the same point.
But why efficacy is not same here?
Oh no, it's not the same here because there is a non-competitive inhibition of some sort.
It is non-competitive inhibition here. You can, it's actually competitive. You can say that way, but it's like why the maximal response is decreased here with a closed pink circle. It's not about inhibition or competitive, non-competitive here actually. I put it in I labeled that to DRC And I said that 100 times till now, like why this dose response curve with the closed pink circle has a submaximal response compared to the left one. Yes, Michael.
They're two agonists of differing efficacies. One's full and the other's partial. They're not being added to each other.
There you go. Simple. So a second one is a partial agonist, so that efficacy is sub-maximal, and this is full agonist, so that efficacy is 100% maximal, so they can produce maximal response. And the second one cannot produce maximal response because it's partial. Period. Period. But they both have high affinity, so the starting point is same. They both can bind to the same ability, but then after a certain point, they will be different because here it is partial, so they cannot occupy all the receptors, and they cannot produce maximal response. Efficacy is less than 100% with partial agonist. Yes.
Dr. Shaw, do you mind if I explain it in a little more simple terms for Mr.
You can go ahead.
So Diego, think about it as making lemonade. Once you put water in the bucket and then you put some lemons, it's a little sour, but then you put sugar and then it's a little sweet. That doesn't mean that the lemonade is not fully active. They're still both there. It's just that one's lowering the other's strength. So you don't taste the sourness of the lemon anymore. But it's still there, so it's a little bit lower, which like the partial. Does that make sense? Don't confuse competitive inhibitors and all that with this. You have to keep them a little bit separate. That's what he was saying earlier. So like if you only have half a tank of gas, you only go so far versus a full tank of gas. Does that kind of make sense? That doesn't mean you don't have gas or that you're hitting the brakes like an inhibitor. Does that make sense?
Yeah, it does. I understand the concept of partial or a partial agonist with limited efficacy. But I was thinking
it's not limited. Don't use the word limited. It's a sub-maximal response. It could have 99% efficacy also, but it would never be 100% efficacy. Diego, it will be less than 100%. It could be anywhere between 0 to 100%. You follow? It's a partial agonist can produce response less than maximal response, period. That's partial agonist, if they both have same high affinity. Partial agonist can go up to here too, but it will never reach to full limit. It can go up to here too. It depends on the nature of partial agonist. But it's not an antagonist to full agonist here, it's a partial agonist. So just don't think that it's because it looks like a non-competitive antagonism. It's not a non-competitive antagonism. It's just two different plots. One is full agonist and the second is partial agonist, and they both have same high affinity to the receptor. All right, anybody else has any questions? Because you guys have done really good job today, and you have a good understanding, good grasp of these concepts now. And do not overthink or overcomplicate the thing, because that can make you more confused. And this doesn't require that much of the overthinking of the overthinker making it overcomplicated. It's very straightforward concept. And I said 100 times that partial agonist has less than 100% efficacy. Period. It will never reach to maximal response. It's partial. Do not memorize again. Try to understand the concept. I've been saying that since beginning of this session or in the last 2 weeks class, that understand the concept rather than just memorizing the fact. It's concept that is important. Okay. Otherwise, you may mix up the things if you just go with the word association or some plot memorization. Do not do that, please. Anybody has any questions? I can stay. Rest of them you can leave, because you guys have done good job, and I think I'm very confident about that. That based on our interactions today and your chat responses, I can see that you understood this concept really well. All you have to do is that you have to make sure that you have to revisit this again. You can rewatch this video with recording. You revisit this everything, all the material again. Understand this concept again. It's volatile. People may forget. So read this material again. Review these resources. Answer. Try to do all the Q banks that I posted on Canvas. Don't miss any learning objective, any information material that I have posted. If you have any follow-up questions, email me, and I'm more than happy to answer their questions. Otherwise, I can meet you on Sunday. Do not overcomplicate. Do not overthink the information. It's not that difficult or complicated. No problem. Thank you, everybody. Thank you for staying back a little late today. I appreciate that.
Yeah.
Anybody has any question?
I do. I just wanted to ask something regarding the I know efficacy. I know under efficacy, just wanted to see if drug response, like the definition of drug response in the end, will only be measured by its final efficacy, or could it also be accounted for on the potency as well? So something like, I don't know if you can see it.
No, I can see it, and I get you. The response is always response is always efficacy. Look at this. It's on the y-axis, DIGO. Basically, you are repeating the same thing what we discussed earlier. You're able to answer that questions actually.